Okay, now we're going to talk about what happens when speed changes, and that deals with acceleration and momentum. So how do we measure a change in motion or a change in speed? So our two learning targets for today, 13 and 14, describe, explain, calculate acceleration, be able to tell the difference between positive and negative acceleration. And the last one, 14, describe how mass affects inertia and how inertia works. Okay, so let's talk about acceleration first. Acceleration is any time an object changes motion. So this means if something is speeding up, that's positive acceleration. If something is slowing down, that's negative acceleration. Also, if it's changing direction. So if you're driving in a car and you make a right-hand turn, that's changing direction, you are accelerating. So remember, speeding up, slowing down, or changing direction are the three ways that you can change speed or motion, and that's acceleration. The formula for acceleration is final speed minus initial speed divided by time, and we'll give you an example of that in just a minute. Okay, one thing I want you to realize is when something is accelerating due to the force of gravity, gravity pulling things down, there is a force that resists motion of falling objects, and that is air resistance. Air resistance that force is greater on an object with more surface area than less. So remember, surface area is how much mass is located on the surface. So let's take a look at a feather versus a penny. Which one has the most air resistance? Which one has the most surface area? The most mass on the surface. That would be your feather. So the feather has the most surface area, has more surface area than the penny. So when they fall, air resistance is greater on the feather than on the penny. So they will not fall at the same time. Oops. So which one will hit the ground first? The coin. The feather is slowed down by more air resistance than the coin. Now, if you put these two objects in a vacuum, meaning there's no air resistance, then they're both going to be pulled down by the force of gravity, which means they will be accelerating at the same speed. That is 9.8 meters per second squared. That is the acceleration due to gravity here on Earth. So if you ask yourself which one is going to hit the ground first, with both of them having no air resistance, then they would hit the floor at the same time because they are accelerating at a speed of 9.8 meters per second squared. This one's rounds it up to 10. Okay, so that's acceleration. Now, the units for acceleration is meters per second squared. The reason for that is if you have speed divided by time, speed is measured in meters per second, divided by time in seconds. You've got two S's, so that's where the squared comes from. Okay, so if I give you an example, let's say the final speed was 10 meters per second, and you started out at initial speed of 0, and it took you 2 seconds to go that fast. So you would take your final speed, which would be 10, minus your initial speed, which is 0, divided by your time, which is 2, and you would get 5 meters per second squared. Now, if the final speed is greater than your initial speed, that means you are speeding up. That means your speed is increasing, so you will have a positive acceleration. But let's say that I told you the final speed was 0, and you start out as an initial speed of 10, and the time was still 2. Then you've got 0 minus 10 divided by 2. That's a negative 5 meters per second squared. That means you were slowing down, decreasing your speed. Okay, so the next target has to do with inertia. So remember, mass is the amount of matter in an object. Inertia is an object's resistance to a change in motion, because sometimes things do not want to accelerate. They don't want to change their speed. They don't want to speed up, slow down, or get it to move or stop moving. So objects with more mass have more inertia. So this little example here, the little car has less inertia than a big truck. So obviously their car broke down, they're trying to push it, and he's trying to look at the bright side saying, well, at least we're in a small car that has a small mass, and has a less resistance to change compared to a truck. Don't want to be trying to push a truck and get it to move. Okay, I thought this was a cute comment for inertia. So remember, this is the resistance to change in motion. So this guy's trying to figure out how to calculate inertia. Meanwhile, the moment of inertia for us is the first nanosecond of summer vacation, of course, because they're just going to sit on the couch. So there's mom saying, I wish you boys would get off that couch. So they have a very high inertia right now, a resistance to move away from the couch now that it's summer vacation. Hopefully you guys are not like that on summer vacation. You don't just sit in front of the TV and play video games. Hopefully we get outside and enjoy the mountains. That's my tip to you. Get outside. Exercise. Okay, so let's get back to inertia. One of the ways that we measure how hard it is to stop an object from moving is called momentum. So it depends on the object's mass and velocity. Obviously, things that are moving faster are harder to stop. And also things that are moving with higher mass are harder to stop. So you've heard of whenever you start taking driver's ed, when you guys get to high school and you start driving, my goodness, you are going to hear a lot of this saying, speed kills. Well, it really does in car accidents. The faster you are traveling, and if there's a car wreck, you're going to have more force. It's going to be harder to stop you from moving, so that's why there's more damage. Also, mass of the car has to do with it as well. You don't want a semi versus that little bug up there. Which one would you rather be in a car accident with? Obviously, you know the answer to that. Momentum does have direction because we have to tell where our object's moving to. To calculate momentum, we use P to stand for momentum. P equals mass times velocity. So the units, mass is going to usually be in kilograms in this instance. Velocity, remember, is meters per second. So the units are kind of long. You just put kilograms times meters per second. So we're going to do an example of how we can calculate momentum and find out how hard it is to stop an object from moving. This is called conservation of momentum. Total momentum of objects that collide is the same before and after collisions as long as outside forces such as friction do not act on an object. Gravity and friction always act on objects, but the effect is small enough, so we're going to ignore them in these examples. So, if I give you this example, we've got Dr. Brown's textbook supply company. This big truck is going to collide with this small bug. Okay, notice the truck has a mass of 20,000 kilograms. The bug, I think I really totally under-exaggerated, is 10 kilometers. I'm sorry, 10 kilograms. The speed of the bus, or the big truck, is 50 meters per second. Speed of the little bug is 0. It's not moving. So this is before the collision happens. So when you do these calculations, the first thing you want to do is find the total momentum before the collision. So total momentum is the momentum of both cars. Now remember, momentum is mass times velocity. So what you're going to do is you're going to find the momentum of both of the cars before the collision and add them together. To do that, we need to take the mass times the velocity of the truck plus the mass times the velocity of the bug. So we're going to take 20,000 times 50 and 10 times 0. So 20,000 times 50 plus 10 times 0 gives me 1 million kilograms times meters per second. This right here is the total momentum of the collision. Okay, so that is pretty important. Remember, total momentum is the momentum of both cars. So then you want to find out what happens after the collision. So now we've got the big truck hitting the bug. And we want to know, okay, when the big truck hits the bug, how fast now is that bug moving? That little tiny car, how fast does it move? So now we have to take our total momentum, which we found before the collision, which was 1 million, okay? That's our total momentum. Total momentum, remember, equals momentums of both cars. So after the collision, we have to find the momentum of both cars to equal total momentum, because the total momentum doesn't change. So to do that, I'm going to look at the mass times velocity for the truck. So the mass of the truck is still 20,000 kilograms. That doesn't change because mass doesn't change. And it's now moving at 10 meters per second. So I'm going to multiply 20,000 times 10 meters per second. I'm going to get 200,000 I forgot to put the units in, but kilograms times meters per second. Then I want to find the momentum of the other car. Well, I know this car has a mass of 10 kilograms, but I don't know how fast it's traveling. I don't know its speed now. So that's what I have to find out. So I'm going to just put a variable in for speed and have that be x. So 10x. So now I've got a math equation that I need to solve for x. So I've got total momentum equals the momentum of the truck, 200,000, plus the momentum of the bug, 10x, because I don't know the speed. So once I do that, I'm going to divide both sides by 200,000 to get rid of the 200,000. Okay, hold on just a sec. Okay, so we want to get 10x by itself. So since over here I'm adding 200,000, I'm going to subtract 200,000 from 1 million. When I do that, I get 800,000 equals 10x. Now I'm going to solve for x. So I'm going to divide this side by 10 and this side by 10. So then I get x equals 8,000 meters per second squared. So that's how fast the bug is moving after the collision. And you're going to get plenty of practice with this. So hopefully after today, after listening to the notes, the video, the notes, you will be able to calculate acceleration, tell the difference between positive and negative acceleration, and calculate how inertia can be calculated using momentum and figuring out how hard it is to stop objects from moving.